Good morning, everyone. My name is Parth Padalkar. I am a PhD student at the University of Texas at Dallas, and today I will be presenting our work, which is using logic programming and kernel grouping for improving interpretability of CNNs. Jumping straight right into the problem statement, what we wanted to look at was how can we generate logical explanations from a convolutional neural network while maintaining high fidelity with respect to the trained CNN model. Now, the objective then is essentially how do we explain what a neural network is learning. Right? Let me go quickly over some motivating arguments behind why we chose this problem. Number one is that convolutional neural networks are popular tools for computer vision tasks. They are being increasingly used for sensitive applications such as autonomous driving, disease diagnosis, etc. And this essentially means that they should not be black boxes, because then there is no way of knowing what they have learned, and it might lead to catastrophic failures based on petty correlations in the data that might have been easily found out only if there was some way to extract the knowledge out and look at it and retrain it again, right, with the appropriate amount of data and the appropriate amount and appropriate type of data. However, as I just said, they are not interpretable, and this is where we wanted to explore how can we generate some sort of logical rules out of the CNN. The key insight in doing that is that the filters or the kernels in the convolution layer of the CNN are known to learn concepts. So the idea, broadly speaking, then is the last layer filters can be represented as predicates that have semantic meaning in a rule set. Before I go into the methodology of the approach that we are proposing, first I would have to cover some preliminaries. One of them, of course, is CNN. A CNN is short for a convolutional neural network, which is nothing but a deep neural net, which is great for image processing tasks, right, or image related applications. One of them is image classification. Right? Now, a CNN has multiple layers, just like any other neural network, and one of the layers is called a convolution layer. And the interesting thing is that a convolution layer has something called kernels or filters, which you can see right here. A kernel is essentially a matrix whose dimensions are predetermined, and this matrix is the one that gets trained as the CNN is trained, and this matrix essentially, or this kernel, learns to recognize concepts in the images as the training goes on. Right? So a fully converged neural network, there will be kernels which will be representing different concepts in the image. Okay. So now how this works is this kernel goes over this input image one stride at a time. Okay. So for example, this blue highlighted image patch is the first one where the kernel will be placed, and then this would lead to a dot product, a pointwise dot product between the kernel and the image patch, and the output would be basically the aggregated value of that pointwise dot product, which in this case is 31. Right? And so on. This kernel will go over the whole image, and this output would be filled in. Another tool that we use in this research is called FoldSEM. FoldSEM is a rule-based machine learning algorithm that learns a decision list in the form of answer set programming rules from a given data set. Now, this is an example of what the rules look like. They will be in the form of defaults and exceptions. And this is a very popular example of what defaults and exceptions look like, or what they look like in terms of a rule set in our ASP. Explies if X is a word and not some abnormal case. This is termed as the exception. X is a word, or word X is the default. Now, FoldSEM generates a very small rule set, and empirically it has been shown to generate a significantly smaller rule sets than a decision tree with higher accuracy most of the times. And the rule set is a stratified answer set program, which means a query-driven interpreter, a query-driven ASP interpreter such as CASP can be used to then pose queries to that answer set program and then also generate justifications as to why a query succeeded. An example rule set that is generated by fold-SEM is shown here. This was the adult income data set, where the task is to predict if an individual earns less than 50k or greater than 50k based on some features. So if you look at the first rule, it is super interpretable, right? X is earning less than or equal to 50k if the marital status is not married with civilian spouse and the capital gain is N1, which is less than or equal to 6849, right? And only with these two rules, fold-SEM is able to get 0.85 or 85% accuracy, 86% precision, which is pretty good. This is an example on the Titanic dataset. Very high accuracy again, and in just two rules, the whole logic of the dataset is captured. Now, coming into the crux of this work. Now, before I go into what our contribution is, first I would have to explain or talk briefly about NeSyFOLD, which is our previous work, in fact, this work is supposed to appear this time at AAAI. And NeSyFOLD is a framework essentially for interpretable image classification. Let me go over what this framework is about. It is a framework for generating rules from a CNN and creating an interpretable model. It can be used for any image classification classification task, excuse me. So how is it done? First, we binarize the last layer filter outputs of the CNN. Then we use the fold-SEM rule-based machine learning algorithm for generating the rules. We label the predicates in the rule set with the concepts that they represent. Remember that the predicates are essentially the kernels in the last layer of the CNN, and they are known to learn concepts. Then we use the CNN and the rules together as a combined interpretable NeSyFOLD model for carrying out the classification task. Here is a pictorial representation of how the rules are generated from a given CNN. First, we have these training images that are fed to the CNN, and the CNN is trained until convergence. Next, the last layer kernels, here denoted from F1 to Fn, are then extracted. Now, the kernel outputs are matrices, so naturally, what we do is we convert those matrices to single values, which are either 0 or 1. So basically, we binarize the kernel's outputs, and what happens then is we get this nice binarization table where each column represents a kernel, right? And each row represents an image in terms of a binarized vector, right? The way to read this is each image is essentially converted to an embedding sort of, where you can tell whether a kernel was active or inactive when a certain image was seen by the CNN. For example, for the first image, kernel F1 or filter F1 is 0, which means it's inactive. Filter 2 or kernel 2 is inactive. Kernel 3 is active, and so on and so forth, all the way till kernel N, which is active. So this is a separate representation that we have changed the image into. And once we have this binarization table, this is the ideal input to the fold-SEM rule-based machine learning algorithm, which very nicely gives us a very succinct rule set using this binarization table, where the rules look something like this, where X the target X is a bedroom if F5X, F1X, and not some abnormal X, right? And now F5 and F1 are kernels that are right here in this table. But this rule set right now doesn't make much sense because we do not know what F5, F1, F2 and all these kernels represent. So the natural step is to semantically label these predicates. Right? These predicates are nothing but these kernels right here. Right? So if F5 is 0 here, then this would be false. The predicate's truth value would be false. Or if it was 1 here, then the predicate's truth value would be true. So now what we need to do is obviously do semantic labeling, and this is another algorithm that we have designed, and I'll go over it as we progress through the slides. But essentially what this does is we get to map each of those kernels with the concepts or concept that they represent. For example, in this case, F5 becomes bed, F1 becomes pillow, so on and so forth. Right? So now you see the rules make sense. X is a bedroom. If there is a bed, there's a pillow, and there's not abnormal 1x. The abnormal 1x is again more conditions and features and concepts. So coming to this work is called NeSyFOLD-G that we are presenting at this conference, and it is an extension over NeSyFOLD. What we have done in this work is that we noticed there is one assumption that we made in NeSyFOLD which is technically not accurate, which is that each filter or each kernel only or each kernel learns a concept, right, or a set of concepts, which is slightly inaccurate. It is known that rather a group of kernels or a group of filters in the CNN are known to learn concepts, right? So in this work, we try to identify groups of kernels, which we call kernel grouping, and then these groups of kernels are then binarized and rules are extracted using them. So the way we do it is add this simple step in between after the binarization, which is we find similar filter groups using cosine-similarity. And then we use fold-SEM, label the predicates, and use the CNN along with the rules to get the new NeSyFOLD model. So in NeSyFOLD-G, here is a pictorial representation of how things happen. We would have these kernels that are extracted, and K1, K4, and K5, after taking the cosine similarity, would presumably be grouped into a single group, which is the red G1 right here. And then K2 and K3 would then probably be grouped together, and this would be represented by this blue group. So notice that in the binarization table this time, each column is not a single kernel, it's a group of kernels. Right? And then once we have this binarization table, we can just throw it to the fold-SEM algorithm, and it would give us these raw rules where every predicate would be dependent on the binarized value of each of these kernel groups in the binarization table. Right? And then once we have these raw rules, we can do the semantic labeling and obtain the concepts that these kernel groups now represent. Right? So so now what we need to figure out is how do we do the semantic labeling of these groups of kernels instead of single kernels. Right? So the semantic labeling of predicates. Just to recall, semantic labeling is labeling all these predicates in the raw rule set, which are kernel groups, as the concepts that they represent. Right, so kernel groups comprise of individual kernels, as we saw, and individual kernels detect some concepts, but groups of kernels tend to detect concepts most of the time. That is generally, whenever a concept is seen, there are multiple kernels that are activated. So the approach that we're going with is to find the particular groups that are being activated. Hence, we need to find the concepts that represent each kernel and then somehow fuse all the concepts of those kernels together to form or to find out what is the overall concept that the group together is representing. And so let's consider a kernel K1 belonging to some group GK. And step 1 is to find some top M images that activate kernel K1 the most. Right? So let's say these are the top M images here that activate kernel K1 the most. And these have been masked with the receptive field of that kernel, which means the area in these respective images in which that kernel is most activated. Right? So the highlighted area in this image, for example, it's this right here, is the area where the kernel is most activated. Another way of saying this is the kernel is looking at this area in this image, it is looking at this area in this image, and this area in this image. Now, as a human, I might go ahead and directly say, hey, this kernel is probably looking at beds, right? But since these are images, we do not know, or the CNN does not know what concepts these are called, right? So we need to input some semantic segmentation masks of those images to our semantic labeling algorithm. Now, these semantic segmentation masks for the data set that we chose for the experiments was provided, which means that for every pixel in these semantic segmentation masks, there is a label saying which concept or which object it belongs to. Essentially, what it means is that we can directly take an intersection with the image above and the corresponding semantic segmentation mask below, and then find out which concepts in this specific region that the kernel is looking at are most predominantly seen. Right? So, for example, in this image, we as humans know that the bed is probably what this kernel is looking at in this image. But when we take the intersection, we will know for sure because we can count the number of pixels that belong to the concept bed and the number of pixels that belong to the concept window. Right? And that is done using the IOU score, which is called the intersection over union score. Right? So when we take the intersection over union score, we would find that bed has the score of 0.4, window has a score of 0.3. Similarly, for this image, bed has a score of 0.8, lamp has 0.1, and so on and so forth for all the images. Now, these are the top M images, which means the images that activate the kernel the most. So that means that we have, all we need to do now is aggregate all these IOU scores together to find out the top concepts that this kernel looks at most of the time. Right? So just take a mean directly of all these values and we end up with this. So IOU bed, IOU window, we have IOU bed 0.5, IOU window 0.3. So this is the IOU score, and turns out bed has the highest score here, followed by window. Right? So this was for kernel K1. We were able to find the IOU scores for kernel K1, but remember our objective was to find the overall IOU score for the group to which this kernel belongs to. So we know that there will be some K1 to Kn kernels belonging to the kernel group GK. IOU K1 is the one that we just found out in the previous slide. Right? These are the IOU scores of all the concepts that kernel 1 was looking at most of the times. This similarly are the concepts for K2. This similarly are the IOU scores for the concepts of Kn. All we need to do is calculate the mean of all these and sort them to get the IOU scores overall of the kernel group GK. So as simple as that, we have a nice metric to determine what concepts the kernel group overall might be looking at, right? And we find that here the forerunners are bed and drawers, right? And with a certain threshold, we can pick either the top 2, top 3, or whatever concepts, whatever number of concepts you want, depending on how accurate or how flexible you are in with your interpretability of those rules, right? So, for example, if you put a margin of 0.2, then you will have, then basically you will be selecting every concept that is in a margin of 0.2 from the top concept. And turns out it's only the one with 0.4 score, which is the drawers concept. Hence, GK will be labeled as bed and drawers, bed1 underscore drawers 1. Right? So now, jumping to the experiments straight away, we used 3 data sets for the experiments. One is the places data set, the other one is the GTSRB, and the last one is the MNIST data set. For the places data set, it has a lot of images of different classes depicting different scenes. We went ahead and we chose only like 2 scenes at a time, 3 scenes at a time, 5 scenes at a time, which we call places 5, and 10 scenes at a time, right? So for places 2, we had bathroom, bedroom. Places 3, we had bathroom, bedroom, kitchen. And then for 5, we had 5 classes, 10, we had 10 classes, so on and so forth. And then for GTSRB, this is a data set that has 43 classes and consists of all or a lot of traffic sign images. So we took this data set as it is, we did not pre-select classes. For the MNIST dataset, we took the dataset as it is again. There are 10 classes in the MNIST dataset, and the task is to predict the digit from the handwritten image of that digit. Right. Now let's take a look at the all the columns up here, all the metrics. Right. So algo represents the algorithm that we used or the framework that we used, which is either NeSyFOLD or NeSyFOLD-G. NeSyFOLD-G is the one where we group the kernels together. NeSyFOLD is the one without the grouping. And the interesting insight that can be seen is that NeSyFOLD-G has almost the same fidelity and accuracy. So I should mention that fidelity is the degree of closeness to the original CNN. Right. So here, for getting these accuracy, fidelity, and all these metrics, we have used the CNN along with the rule set that was generated, and then used them together to do the classification task. So naturally, because we are extracting the rules out, there is some loss in accuracy and fidelity. So that's why you see that the accuracy is not that good, because for places 2, the vanilla CNN accuracy is around 97%, but you see here it's dropped to 93, 92. So there is a loss because of the binarization. Now, fidelity ideally should be 100%, which means that the interpretable model that we've got should be perfectly following the black box model, but it's normally not the case, right? All we can hope for is having as high a fidelity and as high accuracy as possible, right? The pred here represents the number of unique predicates in the rule set. Rules is the number of rules, size is the overall number of predicates in the rule set, total. Right? So the idea is that predicates, unique predicates, number of rules, and the size of the rule set should be as small as possible for interpretability to be as high as possible, while the fidelity and accuracy is also as high as possible. So if you notice, for NeSyFOLD-G, most of the times the fidelity and accuracy is comparable with NeSyFOLD, but there is a very significant drop in the number of unique predicates, rules, and size, which means the interpretability is higher for NeSyFOLD-G. Here is an example rule set that I've taken from the paper itself. This is for the places 3 dataset, which has kitchen, bathroom, and bedroom classes, and this is the justification that was given by CASP ASP interpreter when this query was posed to this rule set, which is target image comma x, and it turns out it gives one model which says image x is a kitchen, and here's the justification of why it is a kitchen, which is pretty cool. To conclude, grouping similar kernels together and then using them to extract rules helps reduce the rule set size, which increases the interpretability. The semantic labeling helps in making the raw rule set more intuitive to understand. The final rules can be scrutinized by experts to look for biases that the CNN might have learned. The CNN can then be retrained with the appropriate data and treated for all sorts of bias reduction. Then the CASP-based interpreter helps because it is a query-driven interpreter and it can give justifications of why a certain prediction was made, and that's very helpful. This framework can also be used for real-world tasks such as interpretable breast cancer detection. And the next step that we are investigating now is how do we propagate this knowledge from the rules that were extracted back to the CNN so that the vanilla CNN can also be trained to mitigate the biases out. These are the references that we used. Thank you so much for listening. If you have any questions, please feel free to email me, and you can ask Dr. Gupta as well. Thank you again, and have a wonderful rest of your day.
Okay, so if hopefully got the idea.
Yeah, let's thank the speaker, although the speaker could not be here. But do you have questions to Gopal, the co-author?
When you go from a filter, you say it's filter number 1 and it represents bad.
Right.
Do you need to go back to image segmentation or something to know that filter 1? How do you exactly know
so that's
that
what you were
filter?
showing the segmenting. So basically
you
you get all the filters and then you take, say, the top 10 images where that filter was invoked, and then you try to determine what this filter is referring to. So that part you can see is very straightforward.
Yeah. Okay.
So it's basically extracting the filters from the last layer, and these filters correspond to concepts. And then you saw we applied the fold-SC algorithm that you heard about yesterday to translate the filters, the classification into rules. And now you need to know what these filters correspond to, and then you can get a rule like, this image is of a bedroom because I see a bed and a pillow, but no sink. Therefore, this must be a bedroom.
No, it's a great idea to look into filters. I once asked my PhD student to look into it, and there were tiny bits in the paper verifying filters. But since they promise to be more abstracted than fully connected layers, it does make sense to look into them.
Right. And then you were saying that basically it's a group of filters that identify a concept. So initially it was, and that helps in reducing the number of rules. Although still in some of the benchmarks, the number of rules is still 30, 40, 50. And it'll be interesting to see, if you feed back the information from the rules, can we reduce the rule size further? Because for us, when we look at something, the rules that run in our mind or the interpretation is actually quite simple. So can we get to an interpretation that is as simple as we come up with?
No, but it's very good that someone looks into filters. Very good.
Thank you. Okay, then let's thank the speaker again and go for the deserved coffee break. Thank you.